Yeah, so greetings to everybody and thank you for the invitation.
Can I introduce you?
Yeah, you can.
I'm happy to introduce Gyula Katona, and he is going to be speaking about sharpenings of the Erdős-Ko-Rado theorem. Take it away.
Okay, so we have a finite set of n elements, and I will use this notation and choose K for the family of all K element subsets of the n element set. And we call a family, a subfamily of this family intersecting if any pair of its members has a non-empty intersection. In picture, this is forbidden. The two K-element subsets, they are disjoint. And the celebrated theorem of Erdős-Ko-Rado from 1961 is that if n is at least 2k, then the maximum size of the family is n minus 1 choose k minus 1. This condition 2k less than or equal to n is important because otherwise you can choose all the k element sets, of course. So, and so of course this bound is sharp as the following construction shows. Fix one point, this red point, and take all k element subsets containing this red point, then they will be intersecting at the red point, of course. Now something else. Choose an integer L, which is at least 2, and take the pairwise intersections and add up the sizes of the intersections. If the family is intersecting, then every such intersection has value at least 1. So, and the number of pairs is L choose 2. So then this sum is at least L choose 2. So this implies this is the question. If this implies the same thing, because this is a weaker condition. If the Erdős-Ko-Rado theorem comes out from this one also, this n minus 1 choose 2 plus 1 is enough instead. And so for this weaker condition implies the result of the conclusion of the Erdős-Ko-Rado, n minus 1 choose k minus 1, but only for large n. Small n is not true. But it turned out, yeah, that let me continue a little bit here. Yeah. So the famous paper of Erdős-Ko-Rado contains a much a more general form of the theorem, but it holds also for large n only. And so we say that the family is T-intersecting if the intersection of any two members have T-element intersection. And this is the general theorem that the size of the family is at most m minus t choose k minus t, and the construction showing that this is sharp is the same thing, that you fix t elements and you take all k elements as containing these t elements. And we found an improvement of this statement too. So if the family is T intersecting, then the intersection for any pairs is at least T, and we have L choose T pairs. So L choose 2 times T is a consequence of the intersecting property. And the question again, is there anything weaker? And the answer is yes, we can decrease it. Namely, we save t minus 1 pieces of the L choose 2, but the last t L minus 2 is decreased to L minus 1 choose 2 plus 1. For a second, let's go back to the previous theorem when t was 1. And question, can we remove the 1 from the bomb? So we started with L choose 2, and we were able to decrease it until to L minus 1 choose 2 plus 1. But one more step, delete the 1. And yeah, you can see here the inequality, what we hope to be sufficient, and try with the picture. So the construction what we had, so if we take only L minus 1 from the construction, so from the sets containing the red point, then they already make this size of total intersection, because we have L minus 1 choose 2 pairs, and every 2 pairs have at least 1. So it means that the else 1, there is no conditional of one more set. So we can choose any set, any key element set, and the condition is still true. So we certainly can increase the size of the family by 1. But can we choose 2 new sets? It's obvious that then we have the intersection, the sum of the sizes of intersections of the L minus 2 sets containing the red point is L minus 2 choose 2. And then we need at least so the remaining pair, because the old ones and the new ones might be disjoint if n is large. So the only pair what we have to consider is the 2 new sets. And so they must contribute with L minus 2, because otherwise, if you add up L minus 2 choose 2 plus L minus 2, we get less than L minus 1 choose 2. So it means that if we choose 2 sets not containing the red point, they must be L minus 2 intersecting. And if we choose many of them, then they all must satisfy this condition, because we choose L minus 2 from the red point, and two other ones, 2 new ones, they must be L minus 2 intersecting. And now continue this, or actually formalize this construction. So we take all the elements containing the element 1, this is the red point, and the k element sets covering the elements from 2 to L minus 1, then this is L minus 2. So, and their number is this, what you can see, this M minus 1 choose K minus 1 plus another smaller binomial coefficient. So we can definitely construct more than N minus 1 choose K minus 1 if we deleted the 1 from the condition. So it is here. This yellow thing has L minus 2 elements. It should be from 2 to L minus 1, but in the picture is different. I'm sorry. Yeah, but what happens if we choose X from the red point and L minus X from the 2? From the new ones, then we get this sum x choose 2 and L minus choose 2 times L minus 2, because every pair has intersection L minus 2, and it's easy to see that this quantity is at least L minus 1 choose 2, so the construction is good, it works. And we conjectured with Katona that this is the best, and I was some few weeks ago in China, and Jian Wang proved it. So it was a conjecture, but it became a theorem. Uh, it is worth mentioning that it is related to a well-known problem of Erdős. Take just the case when L is 3. Then L minus 1 choose 2 will be 1. So then we get this condition that the sum of the three sizes of the intersections is at least 1, which means that we don't have 3 pairwise disjoint k-element subsets. So what is then the maximum? And this was the Erdős matching conjecture. Is for arbitrary L, not for 3 only. That if we don't have L pairwise disjoint uh, k-element subsets, then there are two constructions, which one of them is the best. I have written it's only for k, for L equals 3. And you can see that for large N, he also got this uh, two sum of two binomial coefficients. But this is a very special case when the lower bound is 1. For larger values, L minus 1 choose 2 is more, so it's different. So there is some connection to Erdős matching conjecture. Erdős settled the case when N is large, and if you are interested, Frank and Kupavsky have written a paper which contains all the results for smaller N's 3 years ago. So the general question is now is the following, that we have a family of k-element subsets, and these parameters L and S are given. Also, I should have given some inequalities for them, but not so important. They are obvious, yeah. So, and suppose that for any L L member subfamily, the sum of the sizes of the intersections has size at least S. This is the full question. And so this is infinitely many open questions. Known is, these are known, but you can see that there are jumps here where we don't know. So when we go below L minus 1, choose 2, and when the two intersecting problem we generalize, then we have to go below this one and so on. So now I would like to speak about something else, but it's related. You will see at the end only. But no, because it starts with Erdős-Ko-Rado also. So the beginning and the end are similar. So Erdős-Ko-Rado, what happens if we add one more set? Then of course we know that there will be a disjoint pair. And we proved for another reason, so this was a lemma in our paper, that not only one, but we have n minus k minus 1 choose k minus 1 disjoint pairs. So again, this construction is the best. So all the sets which are disjoint pairs in this construction gives the best. I want to mention that my younger son, he has a PhD in mathematics also, but he's a professor of marketing at Berkeley University. So here I will use the lexicographic ordering of the k-element subsets, and it's actually the characteristic vectors we will order lexicographically. So the characteristic vectors everybody knows, but let me define them. So it's an n element 0, 1 vector. We write 1 if 3 is in the set and 4 is in the set, but we write 0 because 5 is not in the set. And now that it is sometimes discussed what is the proper ordering, which is the beginning and which is the end. But I like this ordering because it is the binary value actually. So it follows the binary value. So it starts with 7, the binary expansion of 7, and then 8, and so on. So increasing the number. So and so consider now in this form the Erdős-Ko-Rado theorem when k is 2. So then it means we have only edges and intersecting edges. Then if n is more than 3, then so it's at least 4, then Erdős-Ko-Rado says that we have a star, so 1 point, we take all edges containing one given point, and so the lexicographic ordering will look like this. I mean, we can choose in this way, that these are actually the last ones in the lexicographic ordering as I defined the ordering. So the four last ones, or in general n-1 last ones. And so when let me see, when n is 5, I'm sorry, when we have n sets, so one more set. So this is what we were starting to investigate, that how many disjoint pairs we have. And in this case, if you take the last ones, you see that the new one, what we added here, this 1 is disjoint from two other ones. And then, of course, the first four ones are not disjoint pairs, so then two. And what if we have one more, so two more than Erdős-Ko-Rado? Then it seems to be true again that the new one has again two such disjoint. Sorry, two. This one is disjoint to this one only. Yeah, one more, so it's three. And or oh, wait a second. Oh, yeah, it's disjoint. The last one, the new one, is disjoint to the second one. So this is why we have four. And so is it true that this is the smallest one? And so the smallest number of disjoint pairs in this case. And the answer is no, because if you take the first six sets, edges in lexicographic order, then you have only three disjoint pairs. And so now the general question is that if we have a family of k-element subsets, and now the number is arbitrary, and number of sets is arbitrary, then dpf denotes the number of disjoint pairs in the family. And the question is that what is the minimum of it? Minimum of that. And in the case when k is 2, it has been solved long ago by Alfred and me that dp, so the number of disjoint pairs, is minimized either for the lexicographically last or for the lexicographically last f sets. So it means edges. So this is very funny that there is it looks in the following way that we have this scale starting from 0, the number of edges from 0 to n choose 2, then until nearly the middle, the last this many edges give the minimum number of disjoint pairs. And in this part, so somewhat after the middle to the end, we have to take the first ones. And here in the middle there are some jumps, but at most 4 times the red and green can change, but always one of them is the best. It's amazing. And quite recently, Dasgan and Sudakov investigated the same question for k-element subsets, and they proved that if n is large relative to k, then the minimum number of disjoint pairs is minimized for the lexicographic last abscess. So exactly the same way as here, but they were able to prove only at the beginning. They have a more precise formulation, but I don't have time to make show the details. So this is the main point. So they also were able to prove the complement here. So they proved that here the last ones, here the new ones, the first ones, and we don't know what happens in the middle. It would be very surprising if in all cases either the last ones or the first ones are the best. And this is where I return to I said that at the end I am again show something similar, because I consider this sum of the pairwise intersections. And so what in Darsgan Sudakov, they formulated, I didn't emphasize it, that, sorry, I didn't emphasize here the jump, so it's minimized for the lexicographically last set, and this should be, this could be also formulated in the way that maximized the number of intersecting pairs. So that is equivalent. So Dasgan-Sudakov, actually, this theorem of Dasgan-Sudakov can be formulated in the way, I forgot to write it down. So the maximum of the intersecting pairs has this property, the same property, but we have to take the complements. And so what we considered, so they, that in the case of Dasgan-Sudakov, they counted only one for every intersection. And we want to maximize now here the sum of the intersections. So if a pair is intersecting with in 10 vertices, then it gets a weight 10. And surprisingly, it is true again at the beginning that this is also maximized for the lexicographic last ones at the beginning. So we don't know the answer for small n when the number of sets is large. So I was too fast, I think.